In the last part of the section 4.5 notes, we took a look at finding domain and range if we were given the graphs of different equations. That is going to be a different process than if we were asked to find the domain and range if we were only given the equation, and that's what we're going to look at now. If you recall from last section, domain and range is really just words for saying what is our independent or dependent variable possibilities. In other words, for domain, what are all the possible x values we could put into this equation or function? In your range, what are all of the possible outcomes for your y values? Now, when you're only given an equation and need to come up with a domain and range, you have to be able to identify whether the equation is a linear equation or a quadratic equation. Linear equation is anything that's going to produce a line, and the basic form of any linear equation is going to be y equals ax plus b. Now, it does not necessarily have to have this b piece in the equation, a constant term, but it definitely has to have some sort of x involved. So if you have a single x in the equation and y solved for on the other side by itself, it's going to produce a line. Some examples are the equations y equals x plus 4, y equals negative 5x, y equals x, y equals 3x minus 8. You see these two in the middle here don't actually have a b term, a number by itself in the equation, but they still will produce a line, so it is considered a linear equation. So if you remember our domain and range, when we were looking at graphs of linear equations, graphs of lines, all of those equations might produce a line that looked something like that, rising from left to right, or dropping from left to right. But either way, if you recall, the domain and range, because there's no limit to how far left or right the graph goes, the domain is going to be negative infinity to infinity, and there's no limit to how far low or high the graph is going to go. So the range is going to be negative infinity to infinity. So for both our domain and our range, we have negative infinity to infinity, all real numbers. So that works whenever you have any type of linear equation other than a horizontal or vertical line. If you remember, when we have a horizontal or vertical line, that is going to have a more specific kind of domain or range depending on which. Now, a quadratic equation is the type of equation that produces the parabolas we were looking at last section of the notes. Parabolas were those either upside down or upside down U or normal shaping U. That kind of just a smooth curve. The general form of any quadratic equation that would produce a parabola is going to look like this: y equals ax squared plus bx plus c. And similar to a linear equation, a quadratic equation doesn't need these last two pieces in it. It doesn't have to have an x term, it doesn't have to have this c value, which would just be some number by itself, but it does have to have an x squared in it in order to be a quadratic equation, to produce that parabola shape. So some examples of that: y equals x squared, y equals 3x squared minus 2. You see this is missing a single x term and a number by itself, it doesn't matter. This is missing a single x term, it doesn't matter as long as it has that x squared in it. Y equals negative 5x squared plus 8x, y equals 4x squared plus 7x plus 1, all of these because they have that x squared term in them, and that's the highest power of x that's in the equation. Those are going to be quadratic equations that produce a parabola, a type of curve. Kind of reminder here. Okay, that's the parabola shape we're talking about. Could be opening upwards or opening downwards. Now, if you remember when we talked about the domain and range of those type of graphs yesterday, because on a parabola it continues to get wider and wider as it opens upwards, or wider and wider as it opens downward, the domain is going to go from left to right forever, from negative infinity to infinity. There is no restriction on how wide that graph would go. So the domain of any quadratic equation, any parabola, is always going to be negative infinity to infinity. The range, however, was more specific depending how high or how low it would go. But in 0306, we don't have to be able to identify that just from the equation. In 0306, the only time you'll be asked to find the range is if you're given a picture of the graph. So all we need to know for now is that if you're given a parabola, a quadratic equation, the domain is going to be from negative infinity to infinity. And we can use that to build on later. So those are types of equations, types of functions, where there really is no restrictions on your domain and range. We have other types of functions we deal with where we do have restrictions on our domain. There are certain x values that we cannot plug into the equation because it would not make it a function. Some of these are, well, one example of this is a square root function. Okay, a function or an equation where we have a square root symbol in the equation, like we do right here. The restriction that is placed on these types of functions is that the value underneath the square root cannot be negative. Okay, if you understand how a square root works, when you're taking a square root of something, for example, like the square root of 25, you're asking yourself, okay, what number times itself equals 25? The answer to that is going to be 5, simply because 5 times itself, 5 times 5 would give you 25. However, if you were trying to square root a negative number, you're thinking, same idea, what number times itself gives you negative 25? The answer is not negative 5, although I'm sure some of you probably quickly thought, okay, that would be the answer. Think about what would you get if you multiplied negative 5 times another negative 5. Negative 5 times negative 5 would give you a positive 25, would not give you a negative 25. Therefore, there is no number, no negative number, that when you multiply it by itself could give you a negative. So you can't square root a negative number just because of that reason. So that's a reminder of why we are going to do what we're going to do here whenever we have a square root equation. So, value underneath the square root cannot be negative. So, in other words, the value underneath the square root must be greater than or equal to 0. Okay, it can be equal to 0 because 0 is not a negative number, and it could be any positive number, which is anything greater than 0. So find the domain of the equation y equals square root of 2x minus 1. The value underneath the square root is 2x minus 1. So whatever we're getting out of that 2x minus 1, it has to be greater than or equal to 0, because that means it's not a negative then. We then just solve this inequality, just like we would an equation. We want to add 1 to both sides of the inequality symbol. Cancel out the 1's over here. That gets us the 2x by itself. Greater than or equal to 0 plus 1 is 1. And then we would divide on both sides by 2 in order to cancel out the coefficient of x. Giving us x by itself. So the result is that x has to be greater than or equal to 1/2 in order for 2x minus 1 to be a positive number, or 0. So that's how we would write it in inequality notation. If you're asked to write it in interval notation, we have to recall that process, which would be if x can be any number greater than or equal to 1/2, that means 1/2 would be the smallest value it could be, and if it can be anything bigger than 1/2, it'd go on forever towards infinity. Infinity always gets parentheses. Since it's greater than or equal to 1/2, we give it a bracket, meaning we include 1/2 as a possible answer. So as long as we plug in any number for x that's from 1/2 on towards anything bigger than 1/2, if we plugged it in here for x, we'd get some value underneath this square root that's either 0 or greater than 0, and then that's fine, because as long as it's not a negative, we could then square root it to find out what our y value had to be. If we plugged in 1/2, that's going to make it 0 underneath the radical. If we plug in anything bigger than 1/2 for x, it's going to make it be a positive number. So either of these two ways is how we would write our answer for the domain. Now, the other type of function where we have a restriction is that of a rational function. And a rational function is kind of just a confusing looking fraction. So let's slide this up. With any fraction, hopefully you remember that you cannot have a 0 for the denominator. You cannot have 0 in the bottom of a fraction because that's essentially like dividing by 0, which you cannot do. And if you ever forget that, try to do that on your calculator. Try to divide any number by 0, you'll get an error screen. So with rational functions, those are kind of crazy looking fractions like this. Well, whatever your rational function is, the denominator cannot be equal to 0. And so that causes this next restriction we're going to look at. So we would take the denominator in this problem to find the domain, y equals 5 over 3x minus 3. Nothing in this problem matters when finding the domain other than looking at the denominator. And we say, I like to write it this way. 3x minus 3 does not equal 0. It can't equal 0 because that would be like dividing by 0. So then we could solve this equation for x to find out what value x cannot be. So you almost treat this not equal to symbol as if it was an equal sign and just solve it, keep bringing down the not equal to symbol. So if we were solving for x, we would start by adding 3 to both sides to cancel out the 3 here, leaving us with 3x on the left hand side cannot be equal to 0 plus 3 is 3. Then to get x completely by itself, we would divide by 3, divide by 3. Because that dividing by 3 would then cancel out the coefficient here, giving us x by itself. So this tells us that x cannot be equal to 3 divided by 3 is 1. So let me write that in there. X cannot equal 1. Pretty much what this is saying for our domain is that x can be any number other than 1. So as long as you have some number that's not 1, that's a fine value to plug into this equation for x. It's part of our domain. How we would write that in inequality notation would then be, if x can't equal 1, well then that'd be like saying x can be less than 1, or x can be any number greater than 1. So that means the same thing there as how I had it written up there. And then maybe one more way of writing it, if you wanted an interval notation, well, saying x is less than 1 is like saying any number from negative infinity all the way up until 1, but we're not including 1 in it, so we put a parenthesis around it. And x is greater than 1, well, that means x can be any number going from 1 on to positive infinity. But we're not including 1 again, so again we have a parenthesis around it. If you recall back from some of the early sections of the homework we were doing, it could be in this interval or this interval. We put that u in between them to mean the union of those two sets, those two intervals. So it could be in this interval or in this interval. As long as you pick a number in one of the two intervals, it's fine for our domain. And that is how then we find our domains if we were just given equations. Basic equations up here don't have restrictions. Square roots and rational functions, fractions, have certain restrictions we have to keep in mind. And in the next section, or next part of 4.5 section notes, we'll take a look at function notation.